Hi everyone, my name is Dolly Cheetah. Welcome to Quantum Ecosystem Conversations, a series dedicated to exploring the people, technologies, companies, investments, policies, and partnerships shaping the future of global quantum ecosystem. When most people hear the words quantum computing, they think about qubits, revolutionary algorithms, and futuristic quantum computers capable of solving problems beyond the reach of today's most powerful supercomputers. Those breakthroughs are certainly exciting. But behind every quantum processor is an enormous engineering effort that often gets unnoticed. Every quantum computer depends on a sophisticated network of enabling technologies, advanced materials, semiconductor manufacturing, cryogenic refrigeration, microwave electronics, photonics, and specialized interconnects. These technologies may not receive the same attention as quantum processors themselves, but without them, scalable quantum computing simply would not be possible. Today's conversation shines a light on one of those essential technologies. As superconducting quantum computers continue to grow from hundreds towards thousands and eventually millions of qubits, one engineering challenge is becoming increasingly important. How do we deliver signals to an environment that operates only fractions of degrees above absolute zero? How do we minimize electrical loss and interference while allowing these systems to become larger and more reliable? These questions have made superconducting interconnects one of the critical hardware challenges facing the quantum industry today. Our guest is helping develop solutions to those challenges. Dr. Gregory Nielson has spent more than 2 decades working at the intersection of microfabrication, microsystems engineering, and emerging technologies. He earned his bachelor's degree from Utah State University before completing both his master's and Ph.D. in micro and nanotechnologies at MIT. Following graduate school, Greg was selected as a Harry Truman Fellow at Sandia National Labs, one of the nation's premier research laboratories, where he later became a member of the technical staff. Greg later served as a chief scientist at Vivint Solar before founding Nielson Scientific in 2017, with the goal of advancing microfabrication beyond the limitations of conventional manufacturing. Today, his team develops superconducting flex cables designed to support applications ranging from quantum computing to semiconductor manufacturing, advanced sensing, medical technologies. Beyond the technology itself, Greg's entrepreneurial journey is equally remarkable. Nielson Scientific has grown by combining innovation with strategic partnerships, university collaborations, and competitive federal research funding, demonstrating how a small deep tech company can contribute to technologies of national and global importance. Today's conversation is about much more than superconducting cables. It's about what it takes to build a breakthrough hardware. It's about commercializing advanced research. It's about entrepreneurship. And it's about strengthening the quantum ecosystem. So let's begin. Today's guest is Gregory Nielson, founder and CEO of Nielson Scientific. Greg is an engineer, inventor, entrepreneur, and advanced technology innovator whose career spans world-class research institutions, national laboratories, renewable energy, semiconductor technologies, and advanced manufacturing. After earning both his master's and Ph.D. in micro and nanotechnology from MIT, Greg joined Sandia National Labs as a Harry Truman Fellow and later became a member of the technical staff, where he developed advanced microsystems for a wide range of applications. He later served as chief scientist at Vivint Solar before founding Nielson Scientific, where he and his team continued to push the boundaries of advanced microfabrication and superconducting hardware for next-generation technologies. Greg, welcome to Quantum Ecosystem Conversations. It's a pleasure to have you with us today.
Yeah, thanks, Dolly. It's nice to visit with you today.
Great. Greg, let's begin with your journey. Can you give us a background about yourself, your education in detail?
As you mentioned, my background is in micro and nanosystems, nanotechnology. Done a lot of work in optics and a lot of combining optics with microfabrication, optical MEMS, that kind of thing, optical electronics. Started working in this area in graduate school back in Boston at MIT. My thesis was MEMS devices with silicon photonics, so waveguides on a chip. This was back during fiber optic bubble background, 2000. And And so there's a lot of interest in that. And so we were doing some interesting things and building some really cool stuff. And I was lucky to be part of a really great research group, great advisor, and really worked with quite a few professors. And it was a neat experience. From there, I went to Sandia Labs. I was a Truman Fellow, which was a great opportunity to they give you 3 years of funding to pursue kind of whatever you want, and that was pretty unique. So I was doing some work for very advanced high-speed MEMS switching, primarily for. And actually, this was the very first time that I proposed something that was quantum related. But back then, in those early days at Sandia, we wound up working with some colleagues at Sandia and David Wineland on a proposal for doing MEMS switching for ion-trapped qubits. It wasn't funded, unfortunately, real foray into quantum related technology. But I worked at Sandia Labs for 11 years, inertial sensing, navigation for GPS denied areas, for example. Also worked in silicon photonics for various applications. Did a lot of work in optoelectronics, applying microsystem ideas to solar cells. And there were some unique advantages there. Built a big program in that, worked with a lot of people in Sandia, outside of Sandia, national labs, universities, and ultimately wound up deciding to take entrepreneurial leave from Sandia to start a company to commercialize those solar technologies. One of my passions, I suppose you could say, is solving really difficult problems, these deep tech problems. And solving it to me means more than just writing a paper, more than just submitting patents to the patent office or whatever. It's actually bringing that solution to people who can use it and need it in a way they can like implement it into their systems. Things were going really well for me at Sandia, but really for me personally, I felt like I needed to take that next step. And so we launched this company, Empower Technology, and it's doing pretty well, actually. Although I left shortly after founding the company for personal reasons, and ultimately became the chief scientist at Vivint Solar, which was great. There's a lot of great experiences, opportunities there, but ultimately wanted to get back into some of the deeper tech problems and solutions. Was drawn to that. 2017, 2018 timeframe, launched Nielson Scientific. So we've done that and developed some additional kind of related proprietary fabrication techniques. And we've been applying those techniques to various challenging technologies and problems, technical problems that are needed. And one of which, of course, is our high-density superconducting flux cables, which address a critical need in quantum computing. And we're really excited about that one. Actually, we're doing some really, really great work.
So when you founded Nielson Scientific, what was your primary vision for the company? Did you start off working on the superconducting flex cables back then?
No, so the primary goal was really around that three-dimensional microfabrication capability. Having worked in microsystems for a long time, and designed a lot of systems and gone through the fabrication of them, microfabrication relies on photolithography, and that's grown up around integrated circuits, silicon integrated circuits, and they're, fantastic, amazing technology. But what photolithography is really a two-dimensional image on a flat surface. And so when you design things with photolithography as the basis of your fabrication technique, it means that you're basically making a two-dimensional structure that you extrude into the third dimension. So it's a limited three-dimensional structure, really like extruded 2D is what people kind of refer to it as. And that's fine. You can do some really amazing stuff with that, but it occurred to me, a long time ago when I was designing a really complicated MEMS device that, man, if you could do something three-dimensional, full freedom to fabricate something three-dimensional, you could do some amazing stuff in the micro realm. And that was what what was the goal is to develop that technology. When we first started, it was just a concept. We can make structures that nobody else in the world can make because of our capabilities.
Amazing. Is there a competitor for you right now? Adjacent technology?
An adjacent technology to that would probably be what's called two-photon polymerization. And this is a technology that I think the first company that really had a tool is a company called Nanoscribe that came out of Europe. And they've done some great stuff, but what they are doing is they're making three-dimensional microstructures, nanostructures even, submicron in polymers. And these are like photo-definable polymers. They can make some pretty cool stuff, and it's impressive. However, everything they do, it depends on the photo-definable nature of the polymers they're working in. So they can only make these three-dimensional microstructures in polymeric materials. That has its place, and it's very useful in some respects. But, but sometimes you want materials that have better mechanical properties than polymers, or different electrical properties or optical properties or whatever. And so what we've developed is a capability to make those kinds of microstructures, three-dimensional microstructures in high quality single crystal semiconductor materials like silicon or silicon carbide or diamond or gallium arsenide, gallium nitride, whatever you want. It is a technique that relies on the semiconductor properties of the material. And so it is semiconductor based, but those materials are amazing.
So for those who are unfamiliar with Nielson Scientific, what problems or the problem statements are you solving today? And what makes your techniques unique?
So our techniques allow us to make things that are hard to make otherwise. And while we have this capability for three-dimensional structures in semiconductors, what we found is that the same tool has the ability to do some interesting fabrication techniques that are a little unusual. And things came up with our superconducting flex cables. So I ran into a researcher from Brookhaven National Lab, was presenting some stuff related to our three-dimensional fabrication, and she asked us if we could do something to make these metamaterial filters for terahertz optics, and it looked like something we could do. So we looked into it, and sure enough, that was something that our capabilities could do. We try to solve problems for people, and so when we talk to people, they have these technical problems that they don't have a solution for. They don't know the technology, they don't have the technology, or they don't have a way to make the structure that they need to solve their problem. And so we try to be very customer focused in that respect, really pay attention to what our customers say and what they need, and then try to solve those problems for them. This led us to this researcher in Brookhaven. She introduced us to some people at Case Western, great partnership there. And they referred us to some people at Slack who needed a high-density superconducting flex cable for a telescope system they were developing. That was about 5 years ago, and we developed these high-density superconducting flex cables. Well, as it turns out, that solution for these telescopes that had these bolometer arrays in cryogenic systems actually addresses a really important need in quantum computing. And so we've been working with now partners to address this challenge that they have. And so I think this is actually an important lesson, is that in business of any sort, whether it's deep tech or whatever, listening really carefully to your customers. They have needs. There's pain points, there's things that are keeping them up at night. How in the world am I going to interconnect all of these qubits that we have planned in our roadmap, for example? And then if you listen carefully to your customers, you can solve their pain points. They love it. And that's what we love doing. So
Great. It's an excellent point. Basically, you're not pushing your solution onto the customers. You are scouting for problem statements from them, and then essentially coming up with developing a solution, and later looking at what are the other adjacent fields that could be applied for, right? Most often in research fields, you come up with a solution and try to force fit it into different unoptimized or a mismatched problem statement. And I think great point that you just talked about, Greg. So
Yeah.
for viewers who might be very new to quantum hardware, what are superconducting flex cables? Why are they important, and what role do they play inside a superconducting quantum computer?
Yeah, well, that's a great question. So this probably is a good time to show a few images. So this shows a picture here. This is an image from Google, this is one of their quantum computers that they built over the last few years. And I mean, it's a very sciencey looking picture, bit of work. And let me kind of describe what you're seeing here. So right down here at the bottom, this is the coldest part of the quantum computer. And this whole system, it goes down into a vacuum chamber and then it's cooled to very low temperatures. And each layer here is a different temperature stage. And right down here, it's kind of buried in all these wires and stuff, is the quantum chip. And this is where the superconducting qubits exist, multiple qubits there. And that's where the computation occurs. But if you look up here, obviously there's a lot more structure going on. And what you see is all of these wires. And these wires, especially down here in the lower temperature regions from about probably this stage on down, are all superconducting coax cables. And there are thousands of them. I mean, thousands of these cables. And these aren't your run-of-the-mill cables that you use to connect up your TV to your cable. They are a coax cable in that sense, but they are actually superconducting. So these cables are pretty expensive, manufactured anywhere from like $2,000 up to $7,000 each. And so when you get thousands of these, this winds up being a very costly system to make. So you have to bring those signals down to the qubit and then back out of the refrigerator to a classical computing chip to interpret what's going on in the qubits and to control them. So the bulk of this really is these kinds of wires. Quantum computer is really impressive. You can do some really amazing things. But the problem is these individual single channel coax cables are not scalable to the numbers of qubits that people need to get to have a fully functional high power quantum computer. They need a different solution, and that solution doesn't fully exist yet. But that's what we're addressing, is this wiring problem of getting the signals from kind of the room temperature classical computing systems down to the qubits and then back out again. And as that scales up, all of that needs to be integrated. And that's what we're working. But that's the problem solving.
You said single qubit would be needing 3 to 5 of these cables. Is that correct?
Yeah, and it's 3 to 5 cables for each stage, each temperature stage. So it really kind of expands out from there.
So, based on the current architecture, what is the maximum amount of qubits that a quantum computer is able to offer?
Yeah, that's a good question. It actually comes down to the cooling power of the system. And what is that issue here is each of these wires, it actually brings in a certain amount of heat from the outside world down to the quantum chip. Now, the quantum chip needs to be 10 to 20 millikelvin, so very, very, very cold. But at that low of a temperature, there's a limited amount of heat that you can pull out, that you can reject out of the system. And so what happens is, because each of these cables has sort of a certain cross-section area, each cable brings down a certain amount of heat, and all of that heat needs to be pulled out. Now, exactly the number of qubits that can be accommodated is a little bit dependent on the refrigeration system and how big and complicated that is. But it's clear that the cross-section area of these coax cables is just too large to scale up much beyond where people are at. It also depends a little bit on the quantum error correction that people are doing. So like one logical qubit is actually a combination of multiple qubits, and it depends on how many physical qubits you need to represent a logical qubit. So it's kind of a complicated question, but like the fundamental issue is how much heat is coming into the system and how much you're rejecting, and then some aspects of the qubits themselves. The cross-section area of each wire pulls down a certain amount of heat. And so to solve this problem, it's not just a matter of integrating all these cables into a single cable. It's also reducing the cross-section area and using techniques that reduce the amount of heat transfer going down the cable.
So if the performance of the qubit remains untouched or unaltered during this process, then you could have zero error that can translate to, for example, 1,000 qubits. Let's just take 1,000 physical qubits is equal to one logical qubit. It's just an equivalency I'm doing. But then it would be linear that way, right? If there was no error in the system. Am I reading that right?
Yeah, I mean that's one technique of fault tolerance for quantum computing is aggregating a number of qubits to represent one. That is especially superconducting qubits where it's relatively easy to make multiple qubits. That's the route they're going. It's usually not 1,000 to 1, but it's many. It's tens at least, maybe 100 to 1, depending on the.
These cables were developed in a different field or for a different application when they were putting this quantum computer together almost a decade ago. Can you talk a bit about that technology that was adopted to build the quantum computers? This one, the legacy one?
Yeah. So like this quantum computer here and essentially all of the quantum computers have been almost like science projects, like hero projects, like we want to demonstrate that this has a path forward, that it works, that we can bring together a certain number of qubits and we can do a quantum calculation. And so these weren't ever meant to be like a production system. They were meant to be, hey, let's demonstrate what is possible. And for that, these have been fantastic. And so what they did was they looked around and they said, okay, well, what kind of components are available to us to make the kind of system that is required for this demonstration? And these superconducting coax cables, and they've been around and used for many years in cryogenic systems for a variety of applications, not just quantum technology. Like, for example, the cryogenic telescopes I was talking about, they have these bolometer arrays that they're looking at very, very faint signals out in space and to really reduce the noise. And then they need to get the signals out. And these superconducting coax cables are great for that. Very low loss, very low noise. They're exactly what's needed for that kind of thing. And so that's why they were adopted for these quantum computers. And now the need is different. So they need something that can scale up. They need something that's more economical to make, and something that actually performs better than these superconducting coax cables for their needs. So and that comes back to like really listening to the customers. And so we've been really fortunate to work closely with some really good customers, really good partners, and we make stuff for them. They give us feedback, and it's been fantastic, really.
Great. So how are your superconducting flex cables going to be uh, replacing what we see here? Um, can you explain a little bit more about that?
Essentially, at each temperature level, our flex cables will take a certain number of these channels and integrate them into a single, and it's almost like a ribbon cable.
Yeah.
But with microscale features, microscale channels, and with a certain length required for each stage. Now, for example, this is a cable that we're making for a partner for a cryogenic system. You get a sense of the scale of the cable by the fingers. I don't have a scale bar in the image, but it's very, very thin, extremely thin, very tiny. This particular one has 72 channels. When we talk about high density, that's what we mean is we're really taking a lot of channels and putting it into a very small area. And what's at the heart of this really is we're using some of our proprietary fabrication tools in some unique ways to enable us to get very fine features and very fine control of features in the superconducting material on top of the polyimide flex material. There's a lot of details that go into it, but that's the essence of it. There's actually multiple metal layers, multiple superconducting layers in here. And you can see kind of the contact points here on this one. This little metallization region, this is an important element. Being in a vacuum, you have to cool down everything and even the cabling. And so that is actually a thermalization pad that gets into close thermal contact with the cooling elements in the system to allow the cable itself to be cooled down as well. These are some other designs that we've implemented for customers. But here in this image, you can see we can create lines and spaces down to a few microns on the feature sizes, which is not typical for flex circuits for what you would make for your phone or something, but is required for some of the features that we're making for our customers.
So is this based off of the photolithography technique that you mentioned, or is this something else?
So we actually there's no semiconductor materials in this cable, but what we found is that by playing with femtosecond lasers and things like that, and by playing with certain parameters, we can very selectively remove the metal, leaving the polymer layers intact. And we can do that to high accuracy over large areas, which is not typically possible with lithography-based approaches. Now, having said that, we do use some lithography in the process, but we use that for larger feature sizes and certain steps that where the lithography works. But other steps, we use our laser system, our kind of proprietary fabrication approach.
Right. So if I understand it correctly, the flex cable that Nielson Scientific is developing could essentially reduce the weight of the quantum computer itself, efficiency of operation. Are we able to realize the full qubit efficiency or information without any loss?
Well, there's multiple issues we're trying to solve at the same time. But one is just all of the mass associated with the wiring right now. There's a thermal problem with that. There's some RF issues that we're also trying to address, and the signals you don't want, eliminating those. Very low RF loss. This is actually really important. Not so much on the control side, but on the readout side, because the readout signal is a small signal. And so you need to be very low noise, very low RF loss. Those are all things we're developing. But the economical fabrication, that's actually crucial. Like if you look at roadmaps of 2029 or something from quantum computing companies and the number of qubits, the cost for the wiring, if you don't do anything about it, is something like $1 billion per computer. And obviously that's not going to work even for the biggest companies, right? And so really what we're doing is we're pushing towards that. Particular cable I showed had 72 channels in it. We're wanting to push that up, and cables with 1,000 channels in it. In the not too distant future, you want to continue to reduce, instead of having all of these cables in here, we just have a little ribbon cable coming down, and that's adequate for controlling 1,000 qubits or something.
So with your current technology, what kind of weight reduction are we looking at? Because it's also about assembly, right? If we were to make a quantum computer in future in a modular, repeatable fashion, efficient like our modern manufacturing, it better be simple than complicated. With your current technology, what's the percentage weight reduction you can anticipate?
We haven't really looked at the weight reduction per se, but what we have looked at is like things like what is the cross-section area reduction in terms of related to like how much heat is coming through. I want to say it was like a factor of 1,000,000 or something like that. I mean, it's a huge change. Like you were pointing out, in this case, you're making all these little connections for every single channel, and that's like going back to the first computers that were built out of vacuum tubes, where each vacuum tube you screw in, and that's one transistor essentially.
Right.
And you know, if you've messed up one vacuum tube, or if it blows out, you've got to go find it. That's just not practical for scaling up from a weight point of view, but also from just like an assembly point of view, or even a reliability point of view. I mean, you could connect all these connections up, you turn on your quantum computer and it doesn't work, and you don't know why, right? I mean, one of these connections maybe you didn't tighten up quite tight enough. We're really trying to get past those practical issues as well of you know, how to scale this up in a way that's manufacturable, but gets the weight down, gets the cost down, gets the thermal load down, and really enables the scaling up. I mean, like we don't want to just make this 100 qubit computer better. We want to make the 10,000 qubit system possible. And that's what we're trying to help our customers with.
Great. That speaks to more on the disruptive innovation front rather than incremental, right? You can
Yeah.
spend the next
Yeah.
5 years doing the incremental innovation of making this computer better, or come up with a brand new architecture or a modality.
Yeah, that's exactly right. I mean, there's some practical issues we're solving, but we think we're on this path of enabling new quantum computer better. Our approach to the cabling enables around that. It's almost like thinking about like advanced packaging for classical computing chips, which has enabled a lot of the really high performance server chips and data center chips. You know, we're kind of enabling a integrated, almost like a packaging solution, I think is a way of thinking about it. Obviously, it's not apples to apples. It is a quantum computer after all, but that's one way of thinking about it. Our intention isn't really to do work on the quantum chip itself, enabling the communication to that quantum chip in the best way possible.
Great. And I'm assuming right now the legacy systems are assembled manually.
Yeah, that's right. Every single one is assembled, and there's different companies providing different components. You know, there's the companies providing the cryostats, the dilution refrigerators, and things like that. There's some companies, sometimes the same companies, providing integrated units of tested coaxial cables like this, so that installing them as units, and that helps them a little bit too. But we need to go way beyond that.
Of course. Yeah. Can you also talk a little bit briefly about what are some of the failure points for these cables?
That's a good question. It's usually it's the connections that are kind of the tricky points, allowing for connectors that are more integrated rather than just a single connector. I mean, you look here, if you look closely, you can see that there's connectors on both sides of this plate, and you have to make those connections in there. And the thing is with cryogenic systems, one of the things that happens obviously when you cool something way down to near absolute zero is certain things shrink. They shrink at different rates. And so what's a nice, good, tight mechanical connection at room temperature may or may not be a good connection at 10 billion Kelvin. And so, but also some design, but it's usually those connectors that are kind of the issue. And so that's one of the things that we are hoping to provide better solutions for, where it's not just like a kind of a screw-on mechanical connection, but it's something a little bit more integrated. It's not always like it fails or it doesn't fail. You know, that's not often the issue. It's like, does it meet the performance requirement? And there's some variation in that. And superconducting materials tend to have some variation in like the the temperature that it goes superconducting or things like that, the quality of the material. And so that's something else that we're looking into and refining as we go along is the quality of our superconducting materials we're using. That's a tricky thing.
Right. No, it talks about thermal cycling of these materials, regenerability. When I say regenerability, it's coming back to their form, right? The form in which they were assembled or manufactured without going through a failure or a fatigue at one point, because these are all metals and polymers that we are looking at. While quantum computing is exciting application, Greg, this technology seems to have parallel application in adjacent fields. So where else do you see opportunities in semiconductor manufacturing or advanced sensing, medical space, or even instrumentation? Can you talk a bit about it?
We've had a number of conversations with potential partners or potential customers of other applications of this, and there's probably two main groups. One is applications at cryogenic temperatures, and then another one is applications at room temperatures. The ability to make really fine featured flex circuits is advantageous even at room temperature. And like, for example, one of the things, we had a project funded by the Army. They were interested in exploring smart contact lenses, for example. And the trick with smart contact lenses is you've got to do sensing, you've got to communicate with the outside world somehow, and you have to do that with minimal or no power. People have been working on smart contact lenses for a while, and usually what they'll do is they'll make some sort of flex circuit using traditional techniques, which is flat, and then they'll kind of bend it around and form it into a contact lens, which tends to be pretty bulky, and they'll maybe put a little battery and stuff in it, or a capacitor or something to store energy and inductively charge it, right? Well, so one thing we did there was instead of using a flat contact lens or a flat, what we did was we just put metal onto a contact lens directly, and we fabricated that metal into a pattern on the curved surface, which enabled more complicated and smaller features and larger design space for the contact lens, smart contact lens. So that was one application that we looked at. There's other things in medical devices, very small scale ones that might be implantable or whatever, where you need a circuit to connect components together, but you want to keep that as small as possible. And because we can do extremely small features, that's another application. Now, in the cryogenic space, there's a number of things that these superconducting cables could be used for that are not necessarily quantum. And I've talked about some of those, like the bolometer arrays for these telescopes. It turns out for those, they want a whole bunch of pixels, and each pixel has a signal that needs to be read out. In fact, we're making some cables for a customer right now that has like 1,000 channels in each cable, for example. We've also had conversations with potential customers to do like single photon, like a CCD camera, except they measure individual single photons per pixel. So very sensitive things. That's not a quantum effect, but it is something that is done at cryogenic temperatures, and you need to read out each one of those pixels. And so in that case, also you need thousands of channels. That's something that we're looking at.
So are the materials composition wise similar to the legacy systems, or you are working with different metals in the periodic table?
So for the superconducting cables, we don't use copper. Copper isn't a superconductor. We use superconducting metals, and we've looked at a few different ones, but primarily we use niobium for that. In the future, we may look at different metals, but niobium is a good one, and it fits well with the needs of quantum computers and some of these other applications. It goes superconducting around 9 Kelvin, and which is a good place for these types of systems. We do use polyimide formulations that were formulated for traditional RF flex circuits, and we do pick formulations that are very low loss, and so we use that directly. We have had some requests using extremely pure materials for both the metal and the polymers. This is actually pretty hard. Pure in the sense that not only are they pure in terms of not having contaminants, but they want them to be pure in terms of the isotope. So they don't want isotopes that might degrade and might emit a neutron, for example. We're not really building that yet, but that was a unique application. And the reason is an isotope that has the potential for radioactive decay. That's a potential noise source for some of these systems, and so they want pure, but they also want.
I'm curious, does this have any similarity to separation of isotopes using particle accelerators, and how are you sourcing your materials? Because some of these are critical materials, so there is a supply chain disruption too. So can you talk a little bit about that?
These isotopically pure materials, we're not really sourcing those yet, just to be clear. In terms of like having very pure niobium, say for the superconductors, that's an important part of our. We do work with some partners, and there are some US-based companies that provide ultra pure niobium. There's at least two that I'm aware of, I believe, and then but a lot of the niobium production, like I don't believe there is a mine in the U.S. that's specifically producing niobium or refining that ore that I'm aware of. I believe Brazil produces some, Canada does some, and China, of course, does some as well. Lower quality niobium is brought into the US, and I believe there are at least two companies doing ultra pure niobium from feedstock coming from other countries.
Speaking of the supply chain part, Greg, you mentioned few countries that you're importing. Now, any of these are strategic materials? Are your customers international, national? You mentioned DoD. Essentially, how do you pivot to these variations in developing your technology?
From a supply chain side, we're not consuming so much of the material now. I'm not too worried yet in terms of like kind of getting adequate material, but obviously we need to have access to material. We know there's a couple of places in the US that provide them. And specifically, we want the ultra pure niobium in the form of a specific sputter target. We deposit the material with sputtering. Once we've made the material polyimide with the niobium and metals on it, we then process that. And it's so the supply chain isn't just the niobium source, it's also all the steps that lead up to us getting the material we need for our processing. And there are some aspects of that we do externally with vendors here in the US, but our goal is to bring more of that in-house because we want to control those portions. Like from a quality point of view, it's much better for us to control some of those steps.
Now, this technology is developed in Salt Lake City, or was it licensed from a different company or a university, or was it developed in partnership with someone?
So we've developed this technology kind of not exactly from scratch. I mean, there's other people who've done high density flex cables. What we've done is we've kind of taken a different approach than what others have done. Typically, what people have done is they've used photolithography of the type that's done with silicon wafers. And what they'll do is they'll spin on a liquid polyimide, they'll cure it, they'll deposit the niobium and whatever else on there, spin on another layer of polyimide, cure that, and they'll kind of go through that process to create the multi-layer flex cable that they need. And people have done some pretty amazing stuff with that. The trick is it's pretty expensive to make flex cables that way. And then you're limited to the size of silicon wafer processing. So currently the very best tools can do up to 300 millimeter or 12-inch wafers, but then that's the size of your cable. You can't make it bigger. We're not limited by that. but we can still achieve the same features. We've had people request cables up to over a meter in length, although we're not delivering those yet. But our capability has the ability to scale the size of wafers. So we've looked at what people have done and what they've published on, and but we've developed our own process. We work really closely with Brigham Young University. They've been fantastic partners with us in the development of this. We've also worked with SLAC on this, as well as Case Western Reserve University on some aspects of it. It's a technology we've developed really here in-house, funded through the SBIR and STTR programs and primarily, but also some NRE funding from partners and companies interested in helping us develop the capability.
Great. So speaking of BYU, what role do they play in the development? Is it more on the lower TRL level? Or?
We own tools that we've built and developed, but in many cases, some of those tools are in laboratory space at BYU, and that's helpful because we can do experiments and processes together with BYU. We can take advantage of students. We can train students actually for our needs as well, which has been great. And then we can leverage the R&D infrastructure at BYU for characterizing what we've made, optical microscopes, SEMs, other characterization tools, and we have partnerships with professors there that are experts in their fields that have provided a lot of insight and value to us over the years. We work really closely with them, and it's been a really good partnership. As a small business, we can't afford to go out and buy these things, and we wouldn't use them 24/7 if we did anyway. So
Right.
It makes sense to use shared facilities like at
Right.
university.
Almost like a timeshare if we have available on these equipment, which are sometimes super expensive, right?
Yeah.
So speaking of, your company has really benefited from SBIR funding, these university collaborations and strategic partnerships. How important have these relationships been to your success, and what advice would you give to other entrepreneurs building advanced technology companies like yours?
These kinds of partnerships are invaluable. I mean, they're invaluable for a startup, a small business, but honestly, I think they're invaluable for no matter what, even if you're at a large company. I didn't realize this as much when I was in graduate school. I was fortunate enough to make connections with a variety of really sharp people in grad school. Then going on to Sandia Labs and working there and working on multiple projects with researchers, both inside the labs and outside, and professors, universities across the country, program directors in the federal government. When the time came, when I launched Nielson Scientific, for example, I had this network of people that I'd worked with and I had respect for, and they had respect for me. And so when I'd approached them with, hey, we're developing a 3D fabrication capability, I want to talk with you about like where this might be useful for you so that we can get guidance into what we should be developing. Had those connections, so they were willing to get on a phone call with me. I could talk through things with them, and I've talked to hundreds of people from my network over the years related to things, and that is fantastic. It's one of the coolest things, I think, as I've gone from like some larger companies to smaller companies and things, is that people tend to want to help you succeed, right? And it's kind of a neat thing about, I don't know, humanity is that people are generally willing to help you out. And I like to pay it forward as well, and I try to help people out where I can. But that network of people has been amazing, exciting, and delightful aspects of starting this company is having those interactions. I kind of love it. So
Great. It's a symbiosis that will probably,
totally,
right?
yeah. I like to feel like I'm providing a lot of value to them, and likewise, they're providing a lot of value to me in a lot of ways. So
Great. So what have been some of the biggest financial and business challenges? We talked a little bit about the technical, but other challenges that you faced, and what lessons have you learned along the way?
That's a good question. So when you are at like a national lab or even a university, wherever, I mean, like it's not the same as being in a company. And for better and worse, right? Like Sandia Labs, the job was very secure, right? I mean, like I the likelihood of me being laid off was pretty slim, and or even being fired was pretty slim. But all the same, like if all my projects failed, there was still other projects for me to work on, and it didn't feel like risky, right? If this proposal doesn't get funded or whatever, then it's okay. I still have work to do and get a paycheck, right? But the thing is in a startup or in a small business, that's not the case, right? So, and in particular, we haven't taken on any outside investments up to this point. But what it's done for us is it's actually helped us to focus very clearly on what do our customers want. Like if we're not delivering something our customers want, we're not going to get paid. And so it's really forced us to interface really closely with our customers who happen to be like program directors in federal agencies or at companies who need a certain thing or whatever. That's a good thing. That's a really good thing. The downside though is that as we're growing and working and developing our capabilities and our core capabilities, trying to be strategic about all that, there are times when we do not know if the next contract's going to come in, right? From my point of view, like that feels like real risk. Yeah, we're good for the next 9 months because we have this contract that gets us to that point. But if nothing comes into that point, then we're going to have to make some big changes. There is a certain amount of stress and anxiety that's associated with that. And two things, I guess, related to that. One is like paying really close attention to your customers. I think if you're providing value, then generally speaking, not always, but the work will come. And then secondly, I've had to really face some of the anxiety that comes from these particular scenarios and say, okay, like really think about, well, what is the worst case scenario and deal with that. I can get sometimes paralyzed by the anxiety that can come with that kind of thing, which doesn't really exist in bigger
In
companies and things like that.
So it's definitely pointing to resource-starved environment in a startup or a small business wherein you're resource-starved in the sense you don't have the right technicians to right funding or the partnerships, and which all dictates, and it's only when you have outside investment may or may not understand the wide variety of applications, the technology that you are developing, right? So you want partners also that are strategic, that will grow with you. It's
Yeah,
a tough choice to find the investors that align with that.
yeah.
But so primarily your funding has been from the federal government and these projects that you work with within the federal government.
Primarily that's where we've gone to. Outside investment is there's nothing wrong with it. In fact, it can be really useful. But the key thing is, I feel like, is that you should know exactly why you're bringing that investment on. Like you should know what you're going to do with that money and why bringing that money in is going to lead directly to an increase in value or increase in production, ideally. And so for a lot of the deep tech stuff that we work on and we develop, for example, the flex cables, there are avenues to get funding, grant programs, or R&D contracts. And there's some value in that. Like let's say I had gone to a venture capitalist and to get money to fund the development of these. That's great, but some of these technical experts within these agencies and programs within the federal government, they actually have a pretty good sense of what's going to be valuable and what's not for the people and the agencies they represent. And what that means is that when we get a proposal evaluated from them, and usually they send it out to experts, there is a reasonable expectation that when you're funded for that, there is a vetting, like a market vetting for the technology that comes along with that. that's valuable. It's valuable to us. It's valuable to them. Now, some VCs are very technical and understand some of that stuff with respect to deep tech, and some are not. I'm not saying that, VCs are great and they do technical due diligence and they go out to experts as well.
But yeah.
But what we found is that going this route has helped focus us on some of the key things. We're looking to scale up production of these flex cables. We may also want and need to reach out to investors to bring in that funding to scale up manufacturing. All of the elements that goes into a robust manufacturing line, and that takes money, right? But in that case, I know exactly why I'm bringing that money in. It's to address needs of our customers who've given us a roadmap of, next year at this time we need so many cables per week production capacity, and that I feel really good about going to an investor and saying this is why we need it.
It's almost like a playbook that you're describing for innovators to de-risk the technology far enough to seek the next level of funding for scaling, right? Which is when the
Yes.
governments will not step in at a
Yeah.
higher TRL level. So I think that is pretty strategic and smart of innovators like you. Like today, what do you need for you to scale up your cables? Is it a resource limitation, technician limitation, workforce, other workforce limitation, capability,
Well,
infrastructure?
yeah, I mean it's a little bit of all of the above. So to make more cables, we're going to need more tools, and some of these tools are proprietary tools that we've built in-house. It's not just we go out and buy a tool from whoever and put it in a line and away we go. We've got all the automation software, all of the components, putting it together, doing calibration, all that stuff. It takes work and it takes time, and we need technicians, we need manufacturing technicians who understand what to do. And, again, we're doing things in a very unique way. It's not like we can go out and hire somebody who knows exactly what we're doing. And so we're developing, training, we're developing our quality system, saying this is the standard way of making this, doing this particular step of the process. And we do it that way every single time until we've identified an improvement, and then we swap that out. But we need to do each of those steps exactly the same way. These are sensitive things that we're making, and if we don't maintain that, then our quality suffers, our yield suffers. We need quality system engineers. We need manufacturing engineers. We need all these people. We need administrative people, experience with some of the challenges of scaling up what is really a deep tech technology. It'd be great to find people like that. Um, Marketing people that have a technical bent. How do you find people who can communicate well something as complex as quantum computing to people who maybe aren't very familiar with quantum mechanics?
And are you the only founder, or do you have co-founders for Nielsen Scientific?
So I'm the only founder. I have a great team, and we've had some people who've worked with the company for a long time. But I'm a sole founder. So
And how many employees do you have currently?
let's see. We have 9 right now, and we have some postings out. I think over the next little bit, we'll be hiring a few more technicians, at least 2 or 3 more engineers, and frankly, I need help on some administrative things as well.
So, who would be an ideal technician? How fast can they be trained? Do they have to be somebody who is hands-on would be just enough for this job?
Uh, um, it would be nice if they had some experience in a clean room environment. Now, a lot of what we do is different than like what you might do in a traditional clean room for
Mhm.
like semiconductor silicon processing.
Yeah.
But some of the way to keep them clean and uncontaminated, just that understanding is important. There are some hazardous chemicals and things that we work with, so people who've maybe been exposed to that, had some training, that's definitely a plus. Although, of course, we do training around that as well. Important. We have lasers, we operate in safe ways, but still having some laser safety or laser experience could be useful. Again, not necessary, but being able to be very detail oriented. There's certain alignment steps between the layers that are really critical. And so being detail oriented and figuring out, okay, is that aligned or not? That's a key thing, but also just detail oriented to do the exact same thing every single time without skipping a step, which we've identified. And so like that kind of attention to detail, that's really important. Probably like my hands tend to shake. I sometimes joke that I wouldn't be the best technician for our company, but things like that, being able to handle things that have fine features and sometimes requires like hand assembly at this stage. Some of these things will be automating in the future, but being able to handle that kind of thing is important at this stage.
So do you yourself show up in the lab putting things together, or you're just the brains behind the standard operating procedures?
I used to show up in the lab. I mean, for a couple of years, Nielson Scientific had a head count of one. We had partners with universities and we had
Right,
students. Actually, one of the things that's been great with students is you can kind of expand or contract your workforce as necessary to a certain
right.
degree. That's very helpful.
Particularly for a
But
small business who don't have to have too many people on the payroll, right?
yeah. So managing that, staying lean. I do go into the lab, but mostly I just because I enjoy the team, and enjoy celebrating with them the successes that we have. And we have engineers now who are really sharp, and they're kind of in the day-to-day details of addressing things, figuring things out, and
So,
passing those on to technicians.
uh, how do you retain the talent? Like, what are your potential risks going where the money is, following the money? Maybe somebody from a different state or different nation would offer you a lab space to scale this up. How do those things happen for this
Well,
technology? Are you there yet or not?
I mean, those things do happen. Talking to some of our partners, we do see people getting poached from, one, you know, from one team to another, or, one quantum team to another. You see acquisitions, a number of quantum computing companies have been pretty active in
Right.
the acquisition space. Part of that is, I think, to bring in expertise, as a way to get high performers that way. Here's my philosophy is around retaining people. I definitely want to make sure that they are participating in the upside of the company.
Mhm.
So, everybody participates in
Mhm.
the equity. It's a different structure of how we're approaching it. Everybody participates
Mhm.
in the upside of the company. The other thing I think that is way more important is the company culture. I'm sure many people have had the experience where you've been in a company where the culture is, there's a lot of politics, there's a lot of backbiting or whatever. That's a miserable place to work.
I know.
And we have some core values that are really actually meaningful. And those include things like service and solutions and respect. They mean something to us, to the whole team. And so what that does is it sets the stage for this is the culture
Yeah.
for Nielsen Scientific. This is who we are. This is how we operate. And it's how we interact with each other.
Yeah.
And it's created a beautiful culture and a wonderful team. They may get poached, they may go off and do something else, but for the most part, the team is really happy. In fact, I think everybody loves being part of the team. And honestly, that's a really satisfying part of my job is creating together with the team that kind of a environment and culture. And I love it.
Great, great. Any developments that excite you for the next few years for Nielsen Scientific and generally this technology at large?
This is a really exciting time for quantum computing. So like we talked about how quantum computing in the past, up until a year or so ago, maybe it was about these hero demonstrations. It was like a science project, and throwing everything you had making a quantum computer that could do quantum calculations with 100 qubits or whatever, and showing quantum advantage. And it's been an exciting time because people have started to show that. If you talk to people, there is this transition from the idea that quantum computers are this unique science project, to this is how quantum or how computing will go in the future. And that is exciting. And being a part of that is just really, really exciting. We love to solve problems for people. And this is right down the road. And so we're really excited about these developments. We're excited to be moving forward with this. And I think one of the things that people don't understand about quantum computing so well is that it's not like classical computing where to double computing power you need an additional, exact copy of a data center. To double the computing power of a quantum computer, you need one more qubit, and that makes all the difference. It's been a pleasure talking with you, Dolly.
Absolutely. And any final advice for the students or engineers and also the investor community that might be watching? Do you have a message?
Quantum, just like any other industry, has needs of every industry, Yeah, it needs the physicists who understand quantum mechanics, to a very fine detail. But that's actually just a sliver of what the industry needs. Like I said, we need manufacturing engineers, we need technicians, we need marketing people, we need, bookkeepers, right? We need accountants. We need a way to figure out the finance side of all of this, all of that, all aspects of business are required. And there's many different ways of approaching that and solving those problems. And I think this is an opportunity to be creative, to really look at where the pain points are and the problems that need to be solved, and think about, hey, am I the one to solve that? I think like any newly launching industry, that's a great time to create a new business and address problems.
Anything for the network at large?
We very much like to partner with people. Let us know. We're very open. We are looking to expand and grow, and would love to make connections and start talking with people about that possibility as well. So,
Greg, thank you so much for joining me today on Quantum Ecosystem Conversation. It's been a pleasure learning about your remarkable journey from MIT to Sandia National Labs and founding Nielson Scientific, helping you solve some of the technical challenges that will enable the next generation of quantum computing. Your story definitely reminds that innovation happens at every level of ecosystem, and that transformative technologies are built not only by the companies that make headlines, but also by engineers, entrepreneurs, risk takers, and disruptors like yourself. Thank you for sharing your expertise, your vision, and passion, and it's been truly an honor to have you today.
Yeah, thank you, Dolly.
Thank you. Great.